Greetings and welcome to MAT315 Applied Mathematics with Differential Equations. I'm looking forward to reconnecting with several of you from past courses and also making some new acquaintances. I think we'll have a lot of fun in this course. In this video, I'll give you a very brief overview of the course and then get started on some actual content. So in this course, we're going to focus a lot on differential equations, which are equations involving an unknown function and one or more of its derivatives, but we're also going to look at some discrete models and do a little bit of probabilistic modeling as well, given time. So the process of mathematical modeling can be thought of as kind of a iterative process where you cast your problem in mathematical form and then you deal with it on the mathematical side, and then you try to interpret and see does it really make sense in the real world. Then you refine your model and you do that over and over again. Here is an example of the evolution of solutions of a system of differential equations. This is actually a predator-prey model like you might have seen in Calc 2, say rabbits and foxes. This is called a phase portrait. And just a cool looking picture. The arrows indicate how the solutions will evolve over time, and this is one particular solution. So differential equations again involve derivatives. So if we know something about how a function is changing, we know that a derivative is a rate of change. If we have information about that, we might be able to get a handle on the function itself. Simplistic model here that governs bank interest as well as other things. If you know something grows at a rate proportional to itself, right? Well, that's like saying that Q prime, let's see, proportional means is a constant times itself, right? Okay. We could write this as dq. So here we don't, this is a derivative. We don't know what here the independent variable is suppressed, but it's, it sounds like it's a time derivative here. So here's another way to write down that equation. Okay, so you've seen this equation in calculus. So we've actually solved the simplest of differential equations in calculus, and you could just by guessing find that the solution is Q is some arbitrary constant times e to the kt, right? So the derivative of e to the kt, well, let's check. So if q is c e to the kt, what's the derivative? Well, the derivative of e to a power is e to the power times the derivative of the power. So it's just going to be k e to the kt. So k. Right? Okay, so let's see. Well, this is q here. So indeed, q prime does equal kq. Here's some other examples. This is a second order differential equation because you got two derivatives there. Here's another second order. Remember, we have different notations for the derivative. We can use the prime notation or the d by dt, the Leibniz notation. So a lot of times we'll be interested in solving these differential equations to figure out what u is or what y is, but often we won't be able, the majority of differential equations are not solvable analytically, and we'll be interested in the qualitative behavior, like what happens over time. Does this cup of coffee cool down eventually? Does it approach room temperature? So on the other side of things, or a similar analogous situation, is where things change discretely. In calculus, it's all about continuous functions, except for when we talk about sequences, which are discrete. But you might have a situation where things don't grow continuously. And here's an example. You could figure out what happens by just iterating this process. Okay, so suppose Q sub n is the population on, after the 10th birthing. So at the n plus first stage, you've got what you had, the number of rabbits that you had, plus 50%, right? So remember, we had the population increases by 50% every 10 days. So this is similar to the situation when you have bank interest that's compounded monthly rather than continuously or yearly. Okay, so on the n plus first stage, you have what you had last stage plus 50% more. So here's your model. This is a discrete model, also known as a difference equation, also known as a discrete dynamical system, also known as a recursion. Okay, so all these terms we'll use interchangeably. With this situation, you can kind of see what the pattern is. So on the first, I guess it's day 10, right? After the first gestation, you've got 1.5 what you had on the 0th initially. And then you've got 1.5 what you had on the first, which is just 1.5 squared, what you started with, and so on and so forth. And you can see the pattern. If you want to make this rigorous, you would use a mathematical induction proof. So you can see the so-called solution here is a function of n. So if you give me n, I can tell you how many rabbits there are going to be, assuming you know how many there initially. That's different than the recursion that we started out with. This does not give us a formula for how many rabbits are there as a function of n. You have to know what q sub n was, right? Which means you had to know q sub n minus 1 and so on and so forth. You had to figure out all these intervening values. So we could generate the solution recursively like this, or we could find an analytical solution. This last thing is the analytical solution. Here's another example. Newton's law of cooling. If you know something, the temperature changes at a rate proportional to the difference of temperatures of the object and the surroundings, you come up with the following model. So here's the difference of the temperature of the object. There's the temperature of the object, U, and the surroundings, T. Here's another systems model that would arise here. If you imagine that in two regions, say Orlando and Tampa, that every year 70% of the people stay in Orlando, but then 40% or 30% move to Tampa. And then in Tampa, you've got these values of the proportions that stay and the proportion that goes. You wind up with a discrete model, which is actually it's a system. And if you've had Math 220 or any linear algebra, you might recognize this as a matrix formulation here, and there are matrix methods for doing these things. So we might be interested in the population in 5 or 10 years or something like that, given initial populations for each of these two cities. Is there an equilibrium where eventually, over time, the populations settle out